Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand you? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientists with me, Sue Marchant, and Dave Ansell. What about stories in the world of science? Because there's plenty going on out there at the moment.
There's all sorts of things. One I thought which was quite cute was some scientists in Texas have made a dragster.
Right.
A normal-sized dragster. This is a dragster which is only a single molecule. It's about 3.3 nanometres wide, so that's 3.3 billionths of a metre wide, and 1.8 nanometres long, so it's a lot smaller than the 10,000th the diameter of a human hair.
How bizarre.
It is really quite bizarre.
I can't even visualise it. Would we need a microscope to see it?
You couldn't see it with a light microscope. It's too small to see it. Even with that, you need a sort of scanning tunneling electron microscope to see it. And I guess you're looking from your mouth, you're about to say why, aren't you?
Yes. Why?
Well, they're in the beginning stages of trying to build machines on this nanoscale. So if you want to, at the moment you make computer circuits by basically making photographs and sort of taking a big thing and making it smaller. There's sort of a limit to how small you can get with that. And so in the long run, you might, if you want to start making very, very small computer circuits, it'd be really cool to have machines which are on the same scale as the computer circuits, which can actually build them for you. And then you wouldn't have to put any effort in. You just make a machine which makes computer circuits for you. So basically it's building things which can, in the long run, manipulate things on a very small scale. There's all sorts of interesting things you can do on a nanoscale. Even things which are using already quite a lot of sunblocks have got very, very small particles in them which block the sun better than others. And you can do all sorts of exciting, interesting things with controlling light and the way it moves around. And making machines on that scale will be useful. And basically they're trying to make something which rolls on that scale, because then you can have something which will stick to a surface. At the moment they haven't got any way of powering it, but there's chemical ways which you could possibly power it. And then you have little machines which drive around on a sort of substrate and do things for you. But that's a long time in the future. At the moment, it's just quite cute.
The nano world. That'll be it, won't it? It'll be nano world.
There's
that nobody will be able to see. How
it's
bizarre.
It's a buzzword in science at the moment.
Yeah, very, very bizarre. Dr. Dave, we have one here from Amy Rostin by email. And she asks, could a parachute slow down a spaceship?
Yes, I think she's wondering whether you could deorbit a spaceship of some kind by basically putting up a huge parachute. And there is some atmosphere out at the sort of, especially the place where the space station is orbiting at the moment, and they have to keep firing their rockets to give them extra height, because they sort of lose height because they slow down and they sort of slowly fall down. They have to fire the rockets and lift themselves up again. And yes, and if you have just a satellite sitting around at 100, 200 kilometres orbit, there's just a minute amount of atmosphere there, and it will slowly slow it down over a period of sort of several years. So maybe 5-6 years, it will slowly slow down and collapse and fall down to Earth. So if you put a huge parachute up there, you'd increase the surface area by maybe 100. So you might be able to do it in a few weeks, a couple of months. But it would involve a very big parachute, and it's actually quite hard to control large structures in space, large light structures, because there's nothing to kind of damp them, and they kind of flap around all over the place. It's far worse than the sort of flag flapping on Earth, because there's nothing to kind of slow them down. Sure. If you've got a satellite up in geostationary orbit at sort of 36,000 miles up, then there's very, very little atmosphere, and the satellites there will stay up for millions of years. You could build a parachute as large as you like, and it wouldn't have any effect. In the long run, it would have an effect, but not in a human lifetime.
All right, that's parachutes. We've got Ian on the phone. Hello, Ian.
Hello there, Sue.
Hiya. Happy New Year to you.
Yeah, thanks very much. Same to you.
All right, what's your question for Dr. Dave?
Hello there, Dave.
Hello.
I would like you to inform me how I should look after a new battery. Now, I don't do a lot of miles. Stop and start. To give you a good service life, I understand you're supposed to keep it fully charged?
Lead-acid batteries are definitely not happier chemically if they're fully charged. I think you can form... Yeah, when they're discharged, they can grow all sorts of strange crystals where they shouldn't be, which can short bits of them out and make them not work nearly as well. So, yeah, just keep them fully charged.
Doing a lot of short runs, Dave, that's not the case, is it?
As in they probably won't be fully charged.
If you take a little bit out of a battery when you start it up, I'm talking about a diesel motor, you do take quite a bit out of it, don't you?
Yes.
Yeah, how many miles have you got? Providing your electrical system is working as it should do, how long would it take your alternator to put that back in so it will become fully charged?
I'm afraid I have to be guessing on this one.
4 miles, 5 miles?
I mean, alternators can... I was actually looking into this for my own car because the alternator was dodgy.
Yeah.
There was a dodgy earth on it, and so it wasn't charging very well. But alternators should be able to, I think, produce definitely more than 30 amps. I guess that's at full revs. And the starter motor can pull kind of a couple of hundred amps. So if you're going fast... then if you're actually driving at a reasonably high revs, then you're going to have to be running the alternator for at least kind of 10, 15 times as long as you took to start it. So a few minutes, I'd have thought. But if on idle, it doesn't charge very much because the engine isn't going fast enough to generate enough voltage in the alternator, I don't think. I mean, how short a runs are you doing?
2 or 3 miles, then it's off for half an hour, then another 2 or 3 miles, stop-start like that.
If it's charging up enough, then if it's not charging up enough in the runs you're doing, then it's going to go flat after the most a week, even if it was new.
So with my stop-starting, if it's swinging the engine over all right, stop-start all day long,
then you must be charging the battery as much as you're discharging it, otherwise it would go completely flat quite quickly.
Right, thanks, Dave. Thanks a lot, Sue.
Take care. Bye-bye. Bye-bye. Let's go next to this one from Mike in Colchester. He said, we de-ice aeroplanes on runways when temperatures are at -5. When you're flying and you look outside and look at inside the aircraft and you see the little onboard information saying -50, why isn't the plane icing up then? Great question. Dave?
There's a couple of things. One of them is to do with where the moisture is and the temperature of the plane. If you're on the ground, the plane plane isn't running, then the temperature of the plane is going to be about the same temperature as the ground, so it could be colder than the surrounding atmosphere, and so dew can fall on it and frost can fall on it. Near the ground, the air can be very, very damp. When you get up very high, the air is very, very cold, and so it can't actually hold very much moisture. And if the plane is a bit warmer than the air around it, then the moisture isn't going to condense and it's not going to form dew, or frost, so you're not going to get a problem with icing. You do get big problems with planes if you fly through a rain cloud where you get water in the rain cloud which is below zero, because you can cool water below freezing point, and until it hits something to nucleate it. So if you need some dust or something to form an ice crystal around, and it can't freeze. But once it does it freezes very quickly. In fact, there's some beautiful pictures, videos on the internet of someone having a bottle of what's called super cooled water and pouring it out onto a table, and it just freezes in front of your eyes. It forms to slush in front of your eyes. It really is sort of freezes the whole bottle in sort of 3 or 4 seconds. So if a plane flies into water which is super cooled, then it will form ice on the plane very, very quickly. And this is a big problem, and lots of planes have crashed because of it, particularly in the past, before they developed ways of de-icing. Old planes tend to have, what they tended to do was have a thing along the front of the leading edge of the wings, which would kind of, like a tube, like a bicycle tyre, which was deflated. And then you'd pump air into it and it would inflate and it would crack the ice. And if you crack the ice at the front of the wing, then the air can get in under it all the way to the back of the wing, and then the fast-moving air tends to kind of crack it off and blow it off. I think modern planes often have heaters along the front of the wings, and they can heat the front of the wings so you can just literally melt the ice off the front of the wings, and the stuff on the back just kind of gets blown off by the wind moving past at 100 miles an hour.
We've got an email question here from Phonopax Wex, who says, if the sun went out, would Earth cool to absolute zero? Dave?
Okay, so the Earth is being heated all the time by the sun, and by the sunlight hitting it, light coming from the sun and warming us up. And we're also losing heat all the time because the Earth is glowing as well. We can't see it. It's in a colour of light we can't see called the thermal infrared. In fact, you're glowing all the time in the thermal infrared.
Thank you.
If you've ever seen the police shows on TV where you got the helicopter and the criminals running away and they're glowing bright white.
Yes.
That's a camera which you can see in the thermal infrared. And so everything is glowing in it, hot things brighter than cool things. And so if you turn the sun off, then the Earth would cool down because it's losing all this heat through radiation, thermal radiation. And in fact, it would keep cooling down until there's some other form of heat which will warm it up. If the Earth was in deep space, the only thing which could really warm it up is the microwave background radiation. So the afterglow of the Big Bang is still there. It's just above 2 Kelvin, so about minus 270 degrees C. So about 2-3 degrees above absolute zero. And at that point, then you get heat coming in from the microwave background radiation from the Big Bang, and the Earth would emit some stuff at the same temperature. So the Earth would end up about 2.7 Kelvin. Because we're in the galaxy, you'll get some starlight which would heat us up a bit, so it'd be a little bit above that, but not very much. So 2 or 3 degrees above absolute zero, probably.
Interesting stuff. Now, Dave from Great Yarmouth has sent an email in. How is coal formed, and why do you get soil layers between the coal? Dave?
Okay, coal is mostly vegetable matter, so trees, ancient trees and things. In the UK, most of it's from the Carboniferous period. The name gives it away. And it tends to be formed it's basically vegetable matter, which is first formed peat. It kind of rots a bit, but it gets buried under some soil. And then it gets crushed and crushed and crushed. And as it gets crushed, all of the kind of water and all the hydrogen parts and the water, it gets driven out of the carbohydrates. Carbohydrates, sugars and cellulose, which makes up most of trees, are made of. And they're made of carbon and hydrate water. Sugar's the same. And if you drive out the water, then all you're left with is the carbon. So coal, when it gets to the end of its process, is really quite pure carbon. And the places where it tends to form are deltas. So this is somewhere where the Earth is dropping slowly. So for some reason to do with tectonic plates, the ground is dropping away below sea level, and you've got a river flowing down. As the river flows down, it brings lots of sediment, so it slowly builds up on the floor. Sediment builds up until it gets to the surface, and trees grow. And normally what happens, the river then goes and flows somewhere else, because in a river delta, the river keeps changing direction, so the river goes and flows somewhere else, and then it drops sediment somewhere else. And then the place you're originally looking at grows trees, and it's got lots of trees. Then it slowly sinks and sinks and sinks until it gets below the sea level. And then you get more sediment drop, then the river might come back over the top of it, and then you get more sediment over the top, which seals off the trees which are buried, old trees which are buried under there, so they don't rot, because no oxygen can get to them. And then this process goes on and on and on again. You have an area which has got a river on it, then it deposits and deposits, and it gets above sea level. Then trees grow, and then it slowly sinks again until it gets below sea level. And you get layers and layers of coal, and then sediment. And sometimes, if it gets very, very deep, you get layers of limestone as well. So where you've got sort of corals and things forming in deep oceans, then if it gets lifted up, then it gets higher and higher again, and you get more trees. You get layers and layers of coal, and so the coal measures all the way. In fact, there's probably some under here, but definitely under the north of England, you've got layers of coal, then limestone, then sort of mudstone, then coal, then limestone and mudstone, again and again and again, sort of hundreds of times.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. Now then, Bernie in Peterborough says, we're using all this grit at the moment to melt the ice, so I wondered with seawater, salt water, what temperature does it freeze at, and how can this be affected by pollution? Thank you, Bernie. Dave?
I think normal seawater freezes at about minus 2 degrees C. So the sea, it wouldn't have to get much colder than that for the sea to freeze if it stayed like that for a long, long time. The thing with the sea is a very, very large lump of water, and the water's kind of being churned around by the tides all the time. So that in order to actually get a layer of ice on the top of the water, you've got to get that surface water down to minus 2 degrees C, which does take a very, very, very long time. And it does happen. It has happened in the UK in the past, but not very often.
All right, scary stuff. Let's keep on the roads at the moment. Tesco Tom says, as we're running out of salt and grit for the roads, why can't we just use sand off the beaches?
Okay, salt and grit do two different things. Grit is basically, if you just little lumps of rock, they kind of stick into the ice and they stick into your car tyres, and so they form a little bit of grit between your tyres and the ice. But the ice is still there. But what's normally when the gritters go out, what they're actually doing is throwing salt on the roads. And salt reduces the melting point of water, which is the reason why seawater melts at below 0 degrees centigrade. And so they reduce the melting point of water, which means that the ice on the road melts, and so there's no ice on the road at all, which is much better than having ice with kind of bits of sand in it. In very, very cold places, the salt doesn't work anymore. It can't reduce the melting point of the ice enough, so it doesn't melt, or it isn't practical, so they do just put grit, sort of sandy stuff. You probably wouldn't use beach sand because it's not sharp enough. You'd probably use some kind of crushed rock. In this country, we can normally get away with using salt.
All right, well, more questions coming up. We've got Pat from Lowestoft on the phone. Hello, Pat.
Evening, Sue.
Hello there. What's your question for Dr. Dave?
My question is this. I was told the planet's been messed up. The ozone layer's been messed up. It's getting hotter and hotter and hotter, and we'll never see snow or ice anymore. And if you like to look out the window, what do you see?
Yes, a bit
So what is happening, please?
Okay, there's two things.
Evening, Dave.
Good evening. The ozone layer is a separate thing from global warming. That was, if you're using old-fashioned spray cans, damage the ozone layer, which protects us from ultraviolet light. And that does seem to be sort of levelling out now. The ozone hole is stopping growing because we've cut out all of the CFCs, which are doing so much damage. But the global warming thing, okay. One thing is that weather is basically quite random. The atmosphere is an incredibly complicated system. So you'd expect some years are cold, some years are warm. So looking at 1 year is never a very good idea, because you're interested in the average over 10, 15 years to actually see a change in the actual climate, because some years are going to be warm, some years are going to be cold. Yeah. The other thing is that whilst it's actually very cold this year here in Britain and Northern Europe, and actually it's been colder than normal in lots of Northern Europe, and a sort of swathe going all the way across Asia to sort of northern China as well, are colder than normal. The northern US, northeastern US is actually much warmer than it is normally, and the Mediterranean is actually warmer than it is normally. So overall, the planet isn't actually any colder. It's just our bit of it is. And global warming is a global effect, so globally it's definitely getting warmer.
They told us we weren't going to see any more snow, didn't they?
Well, possibly if you waited long enough, and if we keep burning fossil fuels for long enough, then we're not going to, or it's going to be very exceedingly rare. But that doesn't mean that we won't in the next 10 years. But in 100 years' time, if we keep going the way we are, I think snow would be very, very, very rare.
Thank you, Pat, very much indeed. Take care.
And you. Bye.
OK, bye-bye. Now, let's go to email again. Bev has sent this one in. Dave, why don't we see the stars from the moon? Because when we look up into the night sky, it all looks very pretty. But if you're on the moon, I don't think you can see the stars, or can you?
A lot of the pictures of the astronauts on the moon, you can't see the stars. And the reason is that if you've ever used a camera, there's the exposure setting. And if you're taking pictures of the sky, I don't know if you ever tried to take pictures of stars in the sky with your camera.
Of course.
I've done it a couple of times. You've got to use an incredibly long exposure because they're really very, very, very dim. And so with my camera at home, you can just about detect them if you use sort of a 4 or 5 second exposure. But normally the pictures of some people doing things on the moon, you've got an astronaut standing in full sunlight wearing a white spacesuit in the middle of the picture. Yeah. And you've got a load of ground in full sunlight in front of you. And in order to take a photo of something in full sunlight, you only use an exposure of, say, 1,000th of a second. So although you can see the stars from the moon, if you take a picture of an astronaut with the stars behind him, the stars are far too dim to be able to see on any exposure which you can see where the astronaut wouldn't be completely overexposed. So if you stand on the moon and you look up, you can see stars. And if you got a camera and deliberately put a long exposure, you could see the stars. But you can't really see stars and astronauts at the same time in a photograph.
Let's go to Andy King on the email now, listening online in Worcestershire. He says, does wood vaporise before it burns? Dave?
It's a very good question. For something to burn with a flame, flames are gases burning. So, and for something you can't form a flame without a fuel being turned into a gas. So you've got a candle that's made out of wax. The wax actually vaporises and boils on the wick. Then you get wax vapour, which reacts with oxygen from the air, which then burns to form water and carbon dioxide. If you heat wood up enough, then the whole thing doesn't evaporate, so you don't get kind of great big long cellulose. Wood's made up of cellulose and lignin and all sorts of very long polymer molecules, huge molecules, which can't evaporate on their own. If you get them hot enough, they do break up, and you get small chunks of them, which will to form gases, and they are flammable. This is actually the process you use when you make charcoal. So if charcoal burning, basically you cook wood, you drive off all the flammable substances, vaporizable substances, all you're left with is the carbon, so the black carbon charcoal in the bottom. And so the wood itself isn't vaporizing, but it does break down and turn into gas. Then what you're left with is charcoal, which if you've had a fire burning for a long time, you've got the same sort of things as if you've had a barbecue. You've got sort of these embers which are glowing really brightly, but without any flames. They're still burning, but they're burning with a solid carbon. Is reacting with oxygen as a solid, and just getting hot and releasing energy. And this doesn't make flames, but it still releases a lot of heat. And if you've ever been told how to cook on a barbecue, that's what you want. You don't want flames.
Oh, no, you want it nice and grey and easy so that you can just cook it good. Derek in Wellingborough has emailed in, Dave, to say, my DAB radio gets very loud, especially when a different section comes on the radio for a short period of time. It seems to be tuned in okay. Is this a fault with my radio or the broadcasting station? Mine never works properly. Dave?
I've noticed something quite similar occasionally with mine. I would guess that it's to do with the levels which they're transmitting at, and they haven't quite got them all exactly the same. I would very much doubt if it was the way digital radio works. I would very much doubt if it was something to do with your reception. When the reception goes odd, it sounds very strange, and it goes odd in a way which you're not used to with an analogue radio, but it doesn't change the volume very much, so I'd have thought it would be to do with the broadcaster.
Now then, here's one to lighten things up a bit. Rob Phillis has emailed in to say, does a plane load of ducks get lighter if they all take off inside? Poor little ducks. Dave?
That is a lovely question.
Isn't it?
If the plane is sealed, so if you've got a sealed tube like a modern airliner,
we'd hope so,
then the way the ducks are flying is by pushing air downwards. So they're pushing air downwards, you get an equal opposite reaction which pushes the duck upwards.
Right.
So inside this plane, you've got a huge amount of air being thrown downwards by these ducks really quite fast, holding them up.
Yep. That's
then going to bounce into the floor and push the floor down.
Right.
And so it's going to apply a force to the floor of the plane, and that's going to make the plane heavier. So if all the ducks are flying just as they take off, then you might get some sort of edge effects. So just as they take off and the air is still accelerating before it hits the ground, then the plane might get lighter. But as soon as that air hits the ground, then it's going to be pushing on the bottom of the plane just as hard as the weight of the duck. So in the long run, it doesn't make any difference.
All right. One last question from Yasser, listening in Canada. Woo! By email, concerning the debate about the search for green energy, can we harvest energy from smokestacks?
So I guess what he's thinking here is you've got lots of hot air rushing up chimneys all over the place in big factories. Could you put a turbine in the chimney which would generate electricity? Yes, it's theoretically possible. The question is it worth doing it, and are there better ways of getting the energy out? My feeling is that whilst you can get energy like that, in order to get a lot of it out, you basically need to make the chimney incredibly long, and you need to make sure the gases going into the chimney were really hot at the bottom. And it's probably more efficient to run some other kind of heat engine, something like a Stirling engine, or in fact the solid-state kind of semiconductor things, which you can glue to a heat difference and take the energy out like that, and then just leave the gas coming out of the flue just hot enough to get up out the top. And I think that would probably get you more energy out. People have used exactly the same idea to make green energy, however. They've built a huge chimney. There's one in Spain, and they were thinking about building one in Australia, but it ran out of money. They wanted to build one which is 1 kilometre high. The one built in Spain is only about 300 or 400 metres high. Basically a big long chimney with a greenhouse at the bottom, a big flat greenhouse. Yeah. The sun heats up the air in the greenhouse. It gets hot. Hot air is less dense than normal air, so it rises. So it rises up through this big long chimney. You put turbines in the chimney, and you can generate electricity. So yes, your idea does work, but I think it works better with renewable energy than it does with things out of smokestacks.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.